So our next speaker is Mr. Jing Li from Wuhan University in China, and the topic is the Beidou high accuracy products from B1C and B2A signals.
Hi everyone, I'm Jing Li from Wuhan University, currently a PhD student. Today I'll present our recent work on BDS3 modernized B1C and B2A signals. This work is done together with Professor Jing, Dr. Sheng Yixu, and Professor Qile Zhao. In this study, we investigate two important bias sources that affect higher currency products: the pilot mixed channel and the signal distortion bias. Let's start with the motivation. BDS3, B1C, and B2A signals provide several advantages over the legacy B1I and B3I signals, including lower noise and better frequency. Because of these advantages, IGS has switched to B1C and B2A as the baseline signals this year. But in current IGS or MGX bias processing, the signal biases at the receiver and the satellite sides are independent. However, in fact, satellite code bias has receiver correlation. The receiver manufacturers adopt different signal modulation methods for the same frequency, and the satellite code biases vary from different receiver types tracking the same signals. The first issue is PX bias. Different receiver manufacturers may track different signal channels. Some receivers like Substantial and Leica track the pilot signals, while others like Tremble and Javada track mixed channels. Although these observations correspond to the same satellite frequency, they are not fully equivalent. As a result, code measurements may differ by several tenths of nanoseconds or even more. When observations from different tracking channels are combined directly, systematic inconsistencies are introduced into satellite clocks and phase biases. Dr. Zhang's research shows that after PX bias correction, the convergence time of Galileo was reduced by 23%. The second issue is signal distortion bias, or called SDB. Unlike the pilot mixer bias, SDB is receiver dependent. Even when two receivers track the same signal component, their hardware implementations may introduce different code distortions. Therefore, correcting only the pilot mixer bias is often insufficient. Residual biases may still remain in the observations. To address these issues, we developed a unified framework. The framework estimates both PX bias and SDBs. Substantial receivers are set as a reference because it is the most deployed receiver brands in current IGS network. We first estimate the PX bias and then the SDBs of other receivers like Leica, Tremble, and Javada are calibrated relative to the reference group, the substantial. Finally, both corrections are applied to generate unified satellite products. To evaluate the contribution of each correction component, we designed 4 processing schemes. Scheme P consists of only substantial receivers, while scheme J1 consists of different receivers, and it contains no further correction. Scheme J2 applies only pilot mixed bias correction, and scheme J3 applies both PX bias and SDB corrections. By comparing these schemes, we can clearly quantify the contribution of each bias component. let's first look at the estimated biases. Several observations can be made. First, BDS3 exhibits significantly larger bias than Galileo, about two times larger than Galileo. Second, scheme J2, the PX correction is insufficient. It substantially reduces the overall bias level, but it fails to eliminate receiver-specific differences. Particularly for Leica and Java receivers. After introducing the SCB correction, these residual inconsistencies are largely eliminated. This suggests that the generic pilot mixed correction alone cannot fully explain the observed receiver differences. Next, we evaluate the satellite consistency. For Galileo, all three schemes produce relatively similar results from 0.09 to 0.07. If two IOV satellites, E11 and E12 are excluded, it reaches to 0.06 nanoseconds. However, the situation of BDS3 is very different. Without correction, the mean clock IMS reaches 0.195 nanoseconds, and with PX correction, it drops to 0.073 nanoseconds, and with the additional SDB correction, it further decreases to 0.066 nanoseconds. This corresponds to roughly a 10% improvement contributed solely by SDB modeling. The same trend can be observed for wide lane UPDs. Large inconsistencies are visible in scheme J1 in the left pictures, and most of them disappear after PX correction in the middle. But the better consistency is achieved only in scheme J3, the right one. These results confirm that SDB remains an important error source of current PPPAR products. Next, we evaluate ambiguity fixing performance. For Galileo, the wide lane fixing rate is stable after PX corrections. You can for BDS3, the BDS3 is highly sensitive to bias modeling. In scheme J2, it improves Tremble-Java, which tracks the X code, but degrades Leica performance. And only in full correction J3, scheme J3 achieves uniform performance, and particularly for Leica receivers, the wide lane fixing rate improves from about 70% to 95%. The Netherlands fixing rate remains consistently high across all schemes and all systems. So finally, we examine PPPAR ambiguity resolution performance. The convergence time improves progressively from J1 to J2 and then to J3. The strongest improvement is observed for BDS3. For full correction, the BDS3 convergence time reduced by about 20 to 44% for Leica and Java receivers. And for Leica, the component convergence time reduced from 32.5 minutes to 20 minutes. And most importantly, after applying the complete correction model, BDS3 achieves a performance comparable to, and in China area, sometimes even better than Galileo. So to conclude, we developed a unified framework to jointly modeling PX bias and SDB bias. And the results show that PX correction removes most inter-channel inconsistencies, while SDB correction will provides further improvement. The SDB significantly improves ambiguity fixing rates and PPP-AR convergence performance. And most importantly, after proper bias modeling, the performance of BDS becomes comparable to Galileo. In the future, we recommend IGS analyze centers to integrate SDB modeling because it is so important to BDS data processing. And in the next BDS satellites, some hardwares will be designed to reduce these bias at the source and to simplify data processing. And that's all. Thank you.